Hello, in today's experiment, we will be determining the equilibrium constant of the reaction Ki plus iodine, which gives Ki3. Now this reaction is a reversible reaction, so we need to determine the equilibrium constant for this reaction. But since all the species present in this reaction are in combined form, we cannot directly measure the concentration of each individual species. So we do this measurement by using a technique known as partition method. So in partition method, we need to perform a different set of experiment through which we will determine the partition coefficient of the reaction or partition coefficient of iodine dissolved in the two layers. So first of all, we need to know what is partition coefficient. Now partition coefficient is usually the amount or ratio of concentration of a compound which is distributed in two immiscible solvents at a given temperature. Now this indirectly gives us the solubility of any solute in two different solvents. So the partition coefficient for any solvent pair will be constant at a given temperature, and it will be same irrespective of the amount of solvent taken or solute taken. So in this experiment, we will perform two sets of experiment, in which first we will determine the partition coefficient of iodine in CCl4 and aqueous layers, and in a second method we will use this partition coefficient to determine the equilibrium constant for the reaction which we told.
In today's experiment, we'll be doing two things. The first one that we'll be doing is the calculation of partition coefficient, and the second one which we'll be doing is the calculation of equilibrium constant. So partition coefficient is defined as the ratio of concentration of a compound in two immiscible phases at equilibrium. So and the second part is calculation of equilibrium constant, and the reaction that we'll be studying is Ki plus I2 gives Ki3, which is a reversible reaction. So the equilibrium constant for this reaction is given by K equilibrium is equal to I3 minus divided by the concentration of I2 and the concentration of I minus. So in this reaction, we have a system of distribution of iodine between an aqueous layer and an organic layer, which is CCl4 here. So and Ki is present in aqueous layer. So in Ki, iodine which is present in the form of I3 minus after combining with Ki reacts with sodium thiosulfate to give 3I minus and S4O6 2 minus, and iodine which is present in this form as I2 also combines with sodium thiosulfate to give 2I minus and S4O6 2 minus. Now we will be preparing the solutions that we require for this experiment. First of all, we will be weighing sodium thiosulfate pentahydrate in order to prepare N by 50 solution, and we will be weighing 0.49 grams. Now we will be transferring this amount that we weighed to this volumetric flask. We will stir the contents. After the sodium thiosulfate has dissolved, we will make up the volume to 100 ml. In a similar way, we will be preparing N by 200 of sodium thiosulfate solution by weighing 0.12 grams. Now we will be preparing N by 10 of potassium iodide solution by weighing 3.32 grams and making up the volume to 200 ml. Now we will be preparing saturated solution of iodine in CCl4 by dissolving maximum amount of iodine which can be dissolved in this given volume of CCl4. This is the saturated solution of iodine in CCl4 that we have prepared. Now that we have prepared all the solutions, we will now proceed with our experiment. Now the first experiment that we will be performing is to determine the partition coefficient of the reaction. So these are the solutions that we have prepared. We have an N by 50 sodium thiosulfate solution, we have an N by 200 sodium thiosulfate solution, a CCl4 and a saturated solution of iodine in CCl4. Now we will be taking out some fixed amounts from these solutions and adding those to this stoppered bottle. We will be adding 20 ml of saturated solution of iodine in CCl4 to this stoppered bottle. Then we will be adding 5 ml of CCl4. Now we will be adding 200 ml of distilled water. Now that we have prepared this solution, we will add a magnetic bead to it. And we will be keeping it on a stirrer for 1 hour. After the stirring for 1 hour is complete, this is how the solution has settled. Now we will allow it to settle for another half an hour. After the solution has settled for half an hour, we will be taking out the aqueous layer and then the organic layer and titrating them separately against the N by 200 sodium thiosulfate solution which we have taken inside this burette. So first we will be taking out 25 ml of the aqueous layer here and then titrating it. So in the first part of the experiment, we prepared a stoppered bottle which contained a fixed volume of saturated solution of I2 in CCl4 and 5 ml of CCl4 and 200 ml of water. After the solution is settled, after stirring for 1 hour and then letting it settle for another half an hour, the aqueous layer and the organic layers are withdrawn and the titrations are carried out. Proper care must be taken when we are withdrawing the solution from this bottle so that the contents, the aqueous layer and the organic layer don't mix up. This is the 25 ml of aqueous layer that we have taken out, and now we will start titrating it against the sodium thiosulfate solution. After adding some volume of sodium thiosulfate solution, when the color of the solution turns pale yellow, we will be adding few drops of starch indicator. After the addition of starch indicator, the color of the solution turns blue, which is because of the formation of starch and iodide complex. Now we will be again titrating it against the sodium thiosulfate solution, and after the color of solution becomes colorless, that will be the end point of titration, and we will note down the titer value. Now that the solution has turned colorless, this indicates the end point of this titration, and we will be noting down the titer value from the burette reading. Now we will again withdraw aqueous layer from that stoppered bottle, and we will repeat this titration 2 more times to get concordant values. Now we will be withdrawing 2 ml of the organic layer from the stoppered bottle and adding it to this conical flask. The lower layer is the organic layer and the one above is the aqueous layer that we had earlier withdrawn. After we have withdrawn the organic layer, we will be titrating this 2 ml against sodium thiosulfate solution, which is of normality n by 50, using similar procedure as we followed earlier for the aqueous layer. We will be adding starch as an indicator and then titrating it and noting down the titer value. The titer values that we obtained after the titration of organic layer and the aqueous layer against sodium thiosulfate solutions will be used to determine the concentration of iodine in both the layers, and then these values will be used to determine the partition coefficient value, which is a ratio of the concentrations of iodine in both the layers. These are the results that were obtained after titrating the aqueous layer, and the volume of sodium thiosulfate which was consumed is mentioned here, and concordant readings were obtained, and the average volume of thiosulfate which was consumed is 3.93 ml when the aqueous layer was titrated against n by 200 sodium thiosulfate solution. Similarly, when the organic layer was titrated against n by 50 sodium thiosulfate solution, these are the values which were obtained as 7.8, 7.7 and 7.6 ml, and the average volume of sodium thiosulfate corresponds to 7.7 ml. After the readings were obtained, the calculations were done to obtain the partition coefficient. So, the reaction for the calculation of concentration of iodine, the reaction between iodine and sodium thiosulfate is given as 2Na2S2O3 combined with 1 mole of iodine to give Na2S4O6 plus NaI. So, after the titration, the calculations are done as follows. The volume of aqueous layer which we took was 25 ml, and the normality of sodium thiosulfate solution was n by 200, and the volume which was consumed was 3.93 ml. So, using the normality equation, which is given by N1V1 equal to N2V2, the normality of iodine in aqueous layer is obtained as 7.8 into 10 to the power minus 5 minus 4 normals, and the molarity. So, the molarity of iodine in aqueous layer is given by twice the normality, which turns out to be 0.016 normals. After this, the titration of organic layer was carried out, which was 2 ml, and the normality of sodium thiosulfate that was used for titration is n by 50, and the titer value is given by 7.7 ml, which was obtained. So, again using the normality relation, we can calculate first the normality and then the molarity of iodine in organic layer. So, now that we have the values of iodine which is present in organic layer and also iodine which is present in aqueous layer, we can calculate the value of partition coefficient, which is I2 in the organic layer divided by I2 in the aqueous layer, and the value of partition coefficient which we obtain here is 96.25. In the next part of the experiment, we will be determining the equilibrium constant of the reaction. For this purpose, we have these three solutions, which is the saturated solution of iodine CCl4 and n by 10 Ki solution. We will be taking out 20 ml of saturated solution of iodine in this stoppered bottle. Now we will be adding 5 ml of CCl4 to it. Then we will be adding 100 ml of Ki solution to that stoppered bottle. Just like we did earlier, we will be adding a magnetic bead to this stoppered bottle and stirring it for 1 hour, and then let the contents settle down for another half an hour. And then we will be titrating the organic as well as the aqueous layers against sodium thiosulfate solution. The second experiment that we carried out was preparing a stoppered bottle containing 20 ml of saturated solution of iodine in CCl4 and 5 ml of CCl4 and 100 ml of Ki. This is carried out in order to determine the equilibrium constant of the reaction of Ki with iodine in order to give Ki3.
So now that we are done with our experiment, so we can see that from the first part of the experiment, we can calculate the partition coefficient of the distribution of iodine between CCl4 layer and aqueous layer. And from the second experiment, we can find the equilibrium constant for the reaction. So since from the second experiment, the titration of aqueous layer will give us the total value of I2, which is present in the form of either I3 minus or I2. And from the titration of CCl4 layer, we can find out the concentration of I2 present in the CCl4 layer. Now since we already have our partition coefficient from first set of experiment, we can find the concentration of I2 in aqueous layer using this partition coefficient. And from these two values, we will get the value of I3 minus present in the aqueous layer. Now since we have the value of I2, I3 minus in our aqueous layer, what we need to determine next is the value of I minus present in the aqueous layer. For determining the value of I minus in the aqueous layer, we will subtract the concentration of I3 minus present in the aqueous layer from total concentration of I minus. The total concentration of I minus will correspond to the concentration of initially taken Ki, which was 0.1 molar. So from this we will have all the values of I minus, I3 minus and I2, from which we can easily determine our equilibrium constant.
After the titration of aqueous and organic layers against sodium thiosulfate solutions having molarity N by 50 and N by 200 respectively, these are the titer values which were obtained. So for the titration of aqueous layer, the titer values are obtained as 7, 6.9 and 6.9 ml, and the average value is given by 6.93 ml. For the titration of organic layer against N by 200 sodium thiosulfate, the values which we are getting are 7.1, 7 and 7 ml, which gives an average value of 7.03 ml. These are the calculations that we will be doing in order to calculate the equilibrium constant. The volume of aqueous layer is 10 ml, the normality of sodium thiosulfate is N by 50, and the volume of Na2H2O3 that we have used is 6.93 ml. Again, using the normality equation, we will be calculating the value of normality of iodine in the Ki layer, which turns out to be this, and then the molarity is given by twice this value, which is 0.0277 molars. Then after the titration of organic layer, which was 2 ml, and again using the normality equation, we can obtain the value of normality of iodine in the organic layer and then the molarity. So as we know, the initial concentration of I minus that we had, which was the concentration of Ki solution that we had prepared, and it is 0.1 normals. Now that we know the total concentration of iodine in Ki layer, total concentration of iodine here corresponds to the iodine which is present in the form of I2 and also the iodine which is present in the form of I3 minus, since both of these will be reacting with sodium thiosulfate solution. After this, we also know the concentration of I2 in the organic layer, which is this. The concentration of iodine in aqueous layer can be calculated because we have the value of partition coefficient which we earlier calculated. So we will be dividing the value of I2 organic with the partition coefficient so that we obtain the value of iodine in aqueous layer, which turns out to be this. So I2 combined in the form of I3 minus is given by the total iodine concentration that we have minus the I2 present in aqueous layer, which we just calculated. Now we can calculate the free iodide at equilibrium, which is given by I minus which we initially had, and then I3 minus. So after subtracting these, we can calculate the free I minus at equilibrium. So we are calculating the equilibrium constant for the reaction Ki plus I2 given Ki3. The equilibrium constant can be written as I3 minus divided by I2 divided by I minus. Now that we have the value of all these concentrations, which are 0.0273, and the value for I2, which is this, and the value for I minus, we can easily obtain the value of equilibrium constant. These are the results of our experiment. So the partition coefficient for I2 in CCl4 water system is calculated as 96.25, and the value of equilibrium constant for this reaction is obtained as 1.026 into 10 to the power 3.
So in this experiment, we see that we can use the concept of partition coefficient to determine the equilibrium constant for a reaction in which the determination of each of the ions or components involved in the reaction is not actually very precise. So partition coefficients helps in determining the precise concentration of each of the components or each of the ion involved in the equilibrium reaction.